Okay, so let's look at 13.2. And let's hope everything behaves today. I can already see the drawing. Okay, 13.2 is talking about relative extrema. Okay, we just looked at a graph from 13.1, and I'm just going to sketch it in here. You already have it in your notes, more than likely. Maybe I'll change it a little bit where we have an endpoint this time. Okay, we can see we have peaks, we have valleys. We've talked about these as increasing and decreasing. These things with a function and applications could represent like a company's profit, or so in that case I would be making money and I would be losing money possibly, right? The peaks and valleys, we could talk about profit and loss. So we could also call these in math terms a relative min or a relative max, and so those are the things that this section really talks about, is now we define those. So those peaks and valleys, we're going to relate those to relative minimum and the relative maximum. So let's first do the relative minimum. Obviously, these are the valleys. And we're going to define this as the lowest value of a function within a region around a point. So we don't necessarily need on our graph, we had values on the one that's already in your notes. We don't necessarily need an actual like x equals 5 or whatnot. Let's just use generic. Let's call this one x sub 1, and we'll have x sub 2 and x sub 3. And so if we're talking about the values and relative minimum, it says the lowest value of a function within a region around a point. So do I have a relative minimum, or how many do I have on this graph? How many relative minimums are there? So it says within a region around a point. So I can say I'm looking over here and here and here. So there's actually, well, this is a minimum, isn't it? You guys were all saying x2. But this is actually a relative minimum, isn't it? Because around this area, this interval, this is going to be like the lowest, right? Okay, but I want you to notice the wording. It says the lowest value of a function. So if I'm talking about x2, and then let's call that x4, so we have something to discuss. If I put down my answer that I have a relative minimum x2, is that actually an appropriate answer? Am I really answering it? Because it says the lowest value of a function. Are function values described by x's or y's? The function value is actually the y, okay? So if I want to say I have two relative minima, then I will say they occur at x2 and x4, but the minimum are actually f of x2, right, the y value, and f of x4. Okay, so you might want to make some notes to the side that says we have two relative minima. And I'm going to write that as at x2, or x equals x2, and at x equals x4. You guys see why both of those are where the minima are occurring? We're looking at regions around the point. Okay, so if I want to say what the minimum would be, so I'm going to put where the minimum values are, or the minimum values of the function, right? are described as, how do we write that? Yep, f of x2 and f of x4. So you need to realize there's a difference between where is the minima, it's at, and x value, what is it? It's the y value. Okay. So if you need to put like a little note down here, value of a function, that's talking about the y value. Okay, so likewise, we can put relative maximum. And of course, it's going to be the greatest value of a function within a region around a point. Okay, and do I have relative maxima? Yes, how many? 2. Okay, so then let's go to the other side if you have space, or put in your notes below for this example. There are 2 relative maxima at, now we've got a taste for this, we're going to say x equals x1 and x equals, good, x sub 3. You can see my equal signs keeps vanishing. Where the maximum values I've of course written f of x sub 1 and f of x sub 3. It keeps vanishing. Stay. Okay, and then you guys know from the last sections we could talk about interval of increasing and decreasing, right? You could write those things. Can you tell me about at the point where x equals x1, what the slope of the tangent line is? Sure. Okay, so perhaps you draw that in. Whoops. Okay, and then let's make a note. What we can actually see, though, is that we are going to have relative extremum at, let's call it a C, because we talked about that being a critical number. So this is a critical number, right? Where x sub 1 is. This is a critical number. Where do you see another critical number? Okay, so you jumped ahead of me, but do you agree x sub 2 is a critical number? Because the slope of the tangent line, or f prime, if we're talking about function f, would equal 0. F prime equals 0. Where else you said?
X sub 3.
Okay, x sub 3. Okay. Keep vanishing on that blue. There we go. Okay, so we've got our critical numbers here. We can actually look and see, hey, each of these critical numbers are relative extrema, and it turns out if you have an end point, that will also be a candidate for relative extrema. So we're going to formalize this. I'm going to give myself a little bit of space on here. So let me add. And I'm going to say if a function f has relative extrema at C, then C is a critical number or C is an endpoint of the domain. So if a function has relative extrema at c, then c is either going to be a critical number, or as we see above here, an endpoint like x sub 4. Okay, something that's important to note, that doesn't mean that, that a function has relative extrema at all critical numbers. Okay, we'll see that. So let's take a look at an example here. Do my little trick. There we go. Does anyone know what this graph is? What function this is a graph of? Yeah, f of x equals x cubed, right? And so if I said last time, can you find the critical numbers, what would you do? You'd do what? I'm going to take the derivative, right? And I'm going to set the derivative equal to 0. So I get the derivative is 3x squared. I'm going to set it equal to 0. And what do I get for the critical number or numbers? Okay. Okay, so that is a critical number. So if I look on my graph, where x is 0, is that a relative min or a relative max? No, it's not. So I'm just trying to show you that you can't go and say, oh, if it's a critical number, it is going to be a relative minimum or max. It says if you have a relative min or max, then C is going to be a critical number or an endpoint. Okay, so it's just to show you don't confuse what we've written up here. All right, let's add a page. Okay, what we're doing in this section is just really continuing on. We're going to find intervals of increasing and decreasing. And all relative extrema. So if you take me through that process, if I'm trying to figure out increasing and decreasing, I'm taking the first derivative, right? I'm setting it equal to 0 or finding out where it doesn't exist, because those give me what kind of numbers? The critical numbers. And then I take the critical numbers, I put them on a number line, right? I check to see, is it increasing or decreasing? And that gives me a determination. So before you actually start doing a problem, let's kind of think about if I want to know the relative extrema. Let's say I put 0 as my critical number on a number line. I test something to the left. We don't want anything too crazy. So I put x equals positive 1, and I test something to the right, negative 1, and something to the right, x equals positive 1. And we put down here, you guys remember doing all this, f prime of x, f of x, and then typically off to the little right-hand side, I put like a factored form, if I can, of my function. I'm plugging into it. Let's just say that I got that this was positive for f prime of x. I would then go in and I would say, well, what's happening to my function then? It's increasing, okay. And on the other side, let's say I got that f prime of x, when I tested x to be 1 into my derivative, I got that it was negative, so that meant that f was decreasing. Okay, so let's think about what this graph looks like. The function then is increasing from negative infinity up to 0, and then it is decreasing. So if this is truly a critical number, and I have that we're increasing and decreasing, what can you conclude about where x is equal to 0? That is a relative. Are we a minimum or a maximum? It's a maximum. So you're just going to kind of go, oh, if we're increasing and then decreasing, that's going to be relative max. So you see we're really doing the same thing as last time. Now we're just determining if that's going to be relative max or relative min, or perhaps neither. Okay, so is that clear how this connects to last time? All right, so I'm going to erase this part here. That's us just talking through and getting ready. So we're dusting off the cobwebs from the last section. And it's really very repetitive as we move forward through the rest of the chapter into curve sketching. So the first function that we're going to work with is going to be x cubed minus 9x squared plus 24x minus 10. Got x cubed minus 9x squared plus 24x minus 10. And we go, oh, this is nice because it's a polynomial, so these are the nicest things to work with. You should immediately think about finding the critical numbers. Am I going to have to worry about where the derivative doesn't exist for polynomial? No, it's going to exist everywhere. So really all I have to worry about is taking the derivative, doing that correctly, setting equal to 0, and solving. So the derivative is 3x squared minus 18x plus 24. You guys agree? Okay. Now what? I'm going to set this to 0. And what do you suggest I do? Perfect. Okay, so let's make this a little bit easier to work with. So let's factor out a 3. The GCF is 3. Okay, so I've got 3 times quantity x squared minus 6x and then plus 8. Is that right? And then you're looking into that trinomial within that set of parentheses, and you're like, hey, I need two numbers that multiply to a positive 8, but they add to a negative 6. So if they multiply to be positive, they're both the same sign. They're either both negative or both positive. And they have to be negative because they add to give you a negative. So you put your x in here, and you have, what did you say? You guys agree? I do too, okay. So if I multiply negative 4 and negative 2, that gives me positive 8. If I add those together, I get negative 6. Okay, this looks good. All right, then this is zero factor theorem. We say, hey, the only way this multiplies to give us 0 is if one of these factors are 0. Well, 3 doesn't contribute, stays a 3. So x minus 4 equals 0, or we have that x minus 2 equals 0. And so we get x equals 4 and x to be 2, right? And what are these called again? Okay, so in the first set of homework for this chapter, 13.1, it'll say what are the critical numbers. That'll answer it. We just built on that today and said, well, these are likely to be the relative extrema. Okay, so the next thing that we do, draw the number line, make sure that you have them related to each other on the number line correctly. So I've got 2 and then 4. I recommend putting the first derivative down here in a factored form. So I'm going to use the 3 and then the quantity x minus 4, x minus 2. And then I'm setting up what I call the template, where I'm going to talk about what's happening to the first derivative, and then that's going to tell me what's going on with the function. So all of this is used to analyze the original function. Okay. And I'm just drawing little lines there so I can keep my work in line. Okay, so we're going to test. We want to see if we're negative or positive on these intervals that we've constructed. And so we're going to test x to be, what do you want to do? 1. You can do 1, you could do 0, right? Okay. And you don't necessarily have to do this, but the 3 is going to be positive, so if you want, you can put that positive on the outside. I'm not even going to bother. If there had been like a negative 3, then perhaps I would have the negative. Okay, so if I plug in 1 into that first set of parentheses, 1 minus 4 gives you what kind of sign? Negative. Okay, so I've got a negative, and then I've got a 1 minus 2, which is a negative. So we get overall that we have a positive first derivative. Is that correct? And then we go, hey, if I have a positive first derivative, I remember what that looked like. That meant the slope of my tangent line was positive. And if I can remember what that graph looked like, my function is then increasing. Yep. Okay. So I'm kind of even just sketching my head. I'm increasing. Okay, let's see what happens on the other side. You can see I put a little red line down here. Curve. Okay, on the other side of this, let's test something. How about 3? Okay. So if I plug 3 into that first set of parentheses, 3 minus 4 gives you a negative, and the next set of parentheses, 3 minus 2 gives you a positive, so I multiply those and I get an overall negative, which means my original function, if I think about what a negative slope of a tangent line looked like, that meant my function was decreasing. If I could spell that, that'd be nice. Okay, so I'm thinking to myself, decreasing. So can we already say what x equals 2 is? It's a critical number, but it's also going to be where we have a local max, right? A local max. Okay. Let's continue. So you guys probably already did it without me. You tested x equals 5. You plug that into the quantity x minus 4, so you're going to get a positive 1. I don't care that it's 1, but it's positive. And then 5 minus 2 is positive. So that means f prime is positive on that entire interval, which means my function is increasing. Okay, so I have decreasing, and then I am now again increasing. Okay, so I've kind of drawn in the thoughts here. What we want are to have intervals of increasing and decreasing, so let's go ahead and do that. So f, we should write it that way, f is increasing over what intervals? Yeah, this is telling me that if I had chosen like x equals negative 1 million, I would still have that the first derivative is positive, which means my function's still increasing. That's right, it's increasing over negative infinity all the way until 2. And then I have another set, so I'm going to put union. And then what's the next set? 4 to infinity. Good, 4 to infinity. I'm going to say f is decreasing over 2 to 4. Okay, so that's like the same thing that we did last time, but now it's a step further, and we say there is a local max. I'll go in that order first, a local max or local maximum. Notice I'm going to underline at. The x tells where it's at, right? There's a local max at which x value? Yeah, good. X equals 2. And let me make sure how I phrase this. It says, and all relative extrema. So we want to find out what the extrema is. So I'm going to say at x equals 2. And now I actually have to find out what that maximum is. So how do I do that? Plug it into the original. Remember, all this is to analyze what f is doing, the original function. So I have a local max at x equals 2. It is whatever f of 2 is. Right? This is all to figure out what's going on with the original function f. And then I go back up to my original function, which was a cubic. And it said I would take 2 and cube it. I would subtract 9 times 2 squared. Right? All I'm doing is taking the original function, which is up in your notes, and I'm plugging in 2 everywhere there was an x. So I get 8 minus 36 plus 48 minus 10. And what do you get? 10. Okay, so I could go back and say the local max is at x equals 2. It is 10. Okay, that is my maximum. It's the y value. It's the function value. Does that make sense? And remember, all of this is to determine what's going on. We're analyzing the function using the first derivative test. So we're analyzing the original function. Now let's do the local min. You guys are probably on a step ahead of me even with this. It's a local min at where? Yeah, we had that we were decreasing and then increasing, so that would be where our local min is. It's at x equals 4, and it is I'm going to find what f of 4 is, right? Someone pull out their calculator. What is it? It's 6. Okay, so we have answered everything on this. So we found intervals of increasing and decreasing, and then we found the relative extrema. So does this seem pretty doable? Okay, it is pretty doable with especially polynomials. So let's get into some where it's going to be a little bit trickier. Any questions? Okay. All right, let's do it again. So the same exact question here. We're going to find intervals of increasing, decreasing, and relative extrema. We're going to use f of x is equal to x to the 2/3 minus x to the 5/3. Now, can you actually talk out and say, well, here's how I approach a problem that asks for relative extrema. I'm going to go through the first derivative test. I'm going to find the what numbers? Critical numbers, which I always do by setting the first derivative equal to 0 or seeing where it doesn't exist. Okay, so let's actually take that first derivative. And you guys were pretty good at these on your exam. You've had lots of practice. So it's just using power rule, right? Okay, so walk me through what the derivative is. 2/3 x. Is that right? Okay, x to the negative 1/3. Okay, minus. And yeah, to the 2/3. Okay. All right, that looks good. Okay, what are we supposed to do again? Find the critical numbers? And so I'm going to set it equal to 0 or see where it doesn't exist. Okay, so I'm going to change color. All right, well, let's do some factoring, maybe. Let's start working at how we would factor out with the x's. So I'm going to show you this technique because when you go to your homework and you see one like this, it will do it in the exact same way. There are obviously other ways. But let's look and say, hey, I can factor out an x to the negative 1/3. So let's factor out, and I'll put a note here in green. We're going to factor out x to the negative 1/3. You can factor out anything, you just have to be able to account for it and make sure that you did it correctly. Okay, so I'm going to factor out x to the negative 1/3. That means that at least from the first set of parentheses, it's very easy to see if I factor out that x to the negative 1/3, I just have the 2/3 sitting there, right? I'll have a minus 5/3. And then the question comes in, what will I have left here? If I factor out an x to the 1/3.
You have x to the 1/3?
So tell me what you do when you take like x times x to the 4th. What does that give you?
You add them.
You add them, right? Okay, so this would be... Okay, so when I multiply x to the negative 1/3, and this is all still scratch work, if I multiply this times x to the something, it has to give me back what I started with, right? Isn't that correct? Which is saying that this has to be... Yeah, so you're going negative 1/3 plus something has to give me 2/3. You guys all with me on that? And I heard the correct answer.
3/3.
Yeah, this has to be a 3/3 or 1. Okay, so put in here, this has to be 3/3, which we know is 1. So over here, where I factored it out, I will now have in the parentheses what? Just an x, yeah, because x to the 3/3 x first. Does everyone follow with that? You can factor out anything. It's just that you have to make sure that when you check it, it's the same thing you started with, right? Okay, so I'm doing this again just as you will see in the homework if you do help me solve this, or in the book. All right. How can I rewrite the negative exponent? This. Okay, so I'm going to put it as 1 over, and we can leave it with we could put it in a radical. It's the cube root, right? Okay, and so let me recopy the rest of that. I really wanted to factor out a 1/3, but I'm doing it just as the book was showing. Okay, so I'm supposed to see where this is equal to 0, or where it does not exist. Anyone see anything? In fact, we can now write this. I don't really like to do it in this way because it's a complex fraction. I can put the 1/3 to the bottom, the 3 on the bottom. This will be the same thing. But you guys agree that this line and this line are the same? Just multiplying them. I can really put that 3 on the bottom. Factor out a 1/3. I'll leave it like that. I put it in this form, this complex fraction, because these are what type of functions? What do we classify this as? It's not a polynomial. We talked about it since the first day of the semester. Rational? And when you see rational, you go, oh, there's something to think about with the domain, right? And where it would be discontinuous, all that good stuff. And so what can't you have? You can't have what, 0? The denominator. So I go and I say, well, first I notice that f prime of x, that's the derivative. We've written the derivative. Does not exist when the denominator, which is x to the 1/3, equals 0, right? Okay, so I want to point that out. So that means that x can't be 0. So I have that x equals 0 is called a critical number, right? Because critical numbers are where my first derivative equals 0 or where it doesn't exist. So I wrote it in this way because I will see that the first derivative won't exist if x is 0. So that's where I have a critical number. I also wrote it in this way because I was like, hey, let's clear fractions. I'm going to say that the denominator here, the way I wrote it, we're going to clear the fractions. So I said we multiply both sides by the LCD, right, if we're actually going to solve it now. So the LCD is just the denominator that you see here. So if I'm starting to solve this, I'm going to multiply both sides by that. And very quickly, I see what I'm really solving is 0 equal to 2/3 minus 5/3 x. I can clear the fractions by multiplying by 3. I don't have to do it in that fashion. However you want to do this. So maybe I decide to clear it again. The denominator is 3, right? 0 times 3 is still 0. If I distribute that 3, right, as long as I do it to both sides, if I distribute that 3, what happens? It cancels, right? That's the point of clearing the fraction. I multiply by the LCD. And so now I'm solving 0 is equal to 2 minus 5x. And then this becomes something easy to solve. So I might write it as 5x equals 2. I'll move the 5x to the left side. And so I get x to be 2/5, right? Okay. So this is where my first derivative is equal to 0, where x is equal to 2/5. So how many critical numbers do I have? This is a critical number because this is where my first derivative equals 0. And I have one from where the first derivative didn't exist. Okay, so this is the first time we've done one like this, right? So then the next step after I have critical numbers is to do what?
Number line.
Number line, okay. So I'm going to have 0, and I'm going to have 2/5. And then I like to put my first derivative in a factored form. So the best factored form I had was when we had it as 1 over x to the 1/3 and then times that quantity, 2/3 minus 5/3 x. Right, this was one way we had it written before we did some algebra. This is when we factored out. Okay, what else am I missing to get going on this? Like, it should be the first things I do before I actually start testing. Yeah, put f prime of x and f of x. Okay, and do you think you can test these? Like if I gave you a few minutes? You doubt it? I heard that. I think you could. Let's just at least decide what numbers we're going to test so we're all doing the same. On the leftmost interval, let's test something to the left of 0. Like -1 would be good. We could do -5, right? We just don't recommend them being too big. And then in between here, what do you want? 1/5, sure. Test x equals 1/5. And then let's all test on the other side, x equals 1. Okay. So I'm going to give you some time to work with your elbow partner for you to work this out on your own. You're going to plug in to the set of parentheses, right, and into this denominator of the factor on the outside. And you're going to determine the sign and then the overall sign. Okay, so let's take a look at this. You were first testing where x is equal to -1. So what I do is I go on the outside here and I'm like, hey, if I take 1 over a cube root of a negative number, so I've got a cube root of a negative number is negative, so 1 over a negative number is still negative. So I've plugged into this outside. I've got a negative. Okay, if I plug in a -1, I'm going to have 2/3 minus 5/3. Well, that's going to clearly give me a negative, so I get an overall. Did I say that wrong? Oh, yes, because it becomes a negative times a negative is a positive, sorry. So it goes 2/3 minus a negative 5/3, so it's 2/3 plus a 5/3, yes. So that's positive, so I get an overall negative, jump in there. Which means that our function, so if you think about what that was, that's the slope of a tangent line that is negative. That meant that our function was decreasing. Okay, good. All right, now if I go and plug in 1/5, which seems weird to do, and it's actually easy without a calculator, if I take a cube root of 1 over 1/5, so it's really taking the cube root of 5, but that doesn't matter. That's still going to be positive. If I were to think about putting in a 1/5 here, notice that the 5's cancel, right? And so I'd have 2/3 minus 1/3, which is positive. And so I get overall positive, which is increasing. Okay, now I go to the other side where x is 1, that's nice. On the outside factor, I'm going to have a positive. If I have 2/3 minus 5/3, so now I'm doing it correctly, I'm going to have a negative, and this gives me an overall negative, which means my function is decreasing. And I'm really hoping that everyone's realizing, like thinking about what that means for the tangent line. The tangent line would have that negative slope, so we can imagine if that graph has to be decreasing on the original function. Okay, so all of this to go on to say, well, this is decreasing, and then I'm increasing, and I'm increasing, and then I am decreasing, right? So what do I have? How did you guys write that? I have a, you want to do local min? I have a local min. You guys can see that's a minimum at where? Okay, at x equals 0. And I say it is f of 0, which is 0, okay? So the value is 0. And this is the one I said, I think 4 decimal places would be okay. So I have a local max at where x is equal to 2/5. And then if I find f of 2/5, so I plug into the original function, let's approximate it to 4 decimal places. What do you have? 0.3257. You guys agree? Okay, so you feel like you could do these? Y'all got those pretty quickly. Any questions on that one? I do have one, and it looks kind of ugly, but it's a good one. I have one more to finish up this section. It's just taking the last section and now just using the words relative max and relative min. No questions? Emily, you have a question? Okay, I'm sorry. I'm going to move that up. Okay, so the next one is application. We are given that the total profit in thousands from the sale of X units or items, whatever we want to call those, is given as units, is given by P of X, which is equal to natural log of negative x cubed plus 3x squared plus 72x plus 1. So this is all in the argument of our natural log. So I have that set of parentheses on there. And it wants to know, and this also, I have to say, this is when we're looking for x in the interval, or x is an element of 0 to 10. So this we're only going to look for when we're making, or we're selling rather, 0 to 10 units. Okay, so this is what the function of the profit looks like for that interval. We're going to find the number of units that should be sold to maximize profit. So before I go any further, I'm looking for the number of units. What variable will I be solving for? Yeah, x gives the number of units. So here we're going to solve for x. We're looking for x. Okay, so has anyone had that thought of, I will just graph this function on my calculator and see where the max is? Some of you did, some of you are shaking your head. Talk about, well, they're not always easy to, if you're given a calculator, first of all, it's not always easy to find the window. In fact, I don't think this one is, to be able to even see it. Like typically it graphs on a standard like negative 10 to 10, right? So this could be tricky to do. But you're doing calculus, and we're going to base this off of the techniques that we've been learning. So if I'm looking for a maximum, right, and I'm looking between the interval of 0 to 10, what I'm going to do is take the first derivative, right? I'm going to figure out where I have critical numbers, and I'm going to test to see where I have a max. Okay, so we're not just going to pull out our calculator and try to graph that thing. It actually may not be that easy. Perhaps I can confirm at the end by my calculator that what I've done is correct, but you will get 0 credit if all you've done is look at a calculator. You guys noticed on the exam I was pretty strict on show all your work. In fact, some of you guys had copies that had it printed twice, show all of your work to receive full or partial credit, so make sure you do that. Okay, so we're going to look for x for that relative maximum value, and I'm going to take the first derivative, and this is where I have to remember my rules of logs, or at least my rules of taking derivatives. So what do I do with this one? Do you remember? Good, 1 over the argument, so that's everything that was in that set of parentheses. And I did notice on the exam I graded, some of you guys would rewrite line by line, like miss something, so be really careful. Okay, so I do 1 over the argument, and then yes, you can put like times the natural log of the base, but here that's natural log of e, and natural log of e is just 1. Okay, and that would have been in the denominator, so we don't have to write that. And now I'm going to multiply by the derivative of the argument, because this is essentially chain rule. Okay, what's the derivative of the argument? Good, negative 3x squared plus 6x plus 72. And so I think this looks a little bit nicer if I go ahead and rewrite it with a nice numerator and denominator. All right, all we're doing is just multiplying across here. Okay, and no one's going to try to cancel anything, right? Like you're not looking at it and then saying, oh, 72 is going to be canceled or anything like that, because you have to be able to factor out a common factor, and it has to be common to both numerator and denominator. So please don't start canceling things. Okay, so I got to look at this, and I've got to find the critical numbers. So what do I do? So I'm going to find where p prime of x equals 0, or where p prime of x does not exist. Okay, so help me out about thinking about that. I kind of like looking at where something does not exist with a rational function right away, right? Because you go, I can't divide by 0. So I really don't want the denominator to be 0. But do we have techniques for solving cubics like readily available to us? Like we're basically saying I can't have the denominator equal to 0, so what you're supposed to do is set negative x cubed plus 3x squared plus 72x plus 1 equal to 0 and then solve for x. Do you think that'll be easy? Probably not. So I want you to think a little bit more. Where did this denominator come from? This was called the argument, right? Okay. What would happen if the denominator or the argument was 0? So that would mean I would have natural log of 0. Is there a such thing? Go to your calculator and type in natural log of 0. It should say error, right? So I'm going to put a note in here. Note, if that denominator, so I'm going to rewrite it because I want to have good, thorough notes. And this is, again, we're looking at where this wouldn't exist, right? If that denominator equaled to 0, we'd have natural log of 0 because this came from the argument. The function doesn't exist, right? You just got an error. Because remember, is this saying like natural log of 0? It's saying e to what power would give you back 0? Does e raised to any power give you back 0? No, it doesn't exist. So I'm going to have here p of x actually doesn't exist when the argument is equal to 0. Okay, so I actually, it's not even in my original domain, so I don't have to worry about it. I'm going to test around it, but it's not actually going to be a critical number. I have to test around it. Okay, so we've settled that part of it. It doesn't even 0 doesn't even exist in my original function. It's not my domain. Okay, so now I need to find out where this first derivative is equal to 0. And so that should be a little bit quicker. When you're looking at fractions, we've already talked about this. You would multiply both sides by the LCD. So what really ends up happening is you're only looking to see where the numerator equals 0, right? That's all you have to do. Because the only way a fraction will reduce to 0 is if you end up with 0 in the numerator. So I could go ahead and I could write in, well, to solve this, I'm going to multiply both sides by the denominator. But what's going to happen to that left-hand side? It still equals 0. That's what I'm saying, that denominator is not going to contribute here to a solution. I could really just go in, straight in, if I've already thought about where I wouldn't exist in this first derivative. I can actually go ahead and say, let's just set the numerator equal to 0. Okay, so for just the sake of showing my notes this time, we're going to have that in there. Okay, so I've got 0 is equal to the numerator, which is negative 3x squared plus 6x plus 72. Okay, we have very readily, easily usable techniques for quadratics. We're going to factor out, how about a negative 3? Good. And then I'm going to have what in the parentheses? X squared minus 2x minus 24. I agree with that. Okay, so I got my -3. What does that factor into? Okay, x minus 6 and x plus 4. Okay, so I'm going to get, what are my solutions? Okay, and all of this was done to find what? Critical numbers, which is where my relative extrema would be. So I can actually conclude the question said to find the relative maxima. I'm going to have to test to see if I have a maxima. But can I throw out one of these solutions right away? Which one? Why? That's right. This is not in the domain that I'm looking at, or the interval, right? X has to be between 0 and 10. We actually found out that 0 doesn't work, right? Okay, so I just have to test using my calculus techniques that where x is equal to 6, I actually will go from increasing on the left to decreasing on the right. I have to make sure that this is a max. Otherwise, I could just say, oh, I really messed up. So let's take our factored form. Write it off to this side, set up our basic template. I have all these things in front of you. I'm just rewriting it. We're testing p prime of x and p of x. Down there we'll have our result. And so what do we want to test? What values of x? You could do 1, you could do 0. I like 0. That would make it real easy. And something to the right of 6. Sure, 10 works. Okay. Okay, 0 is super nice with this one, right? So if I plug in x to be 0, in the numerator you'll have a positive 72, and the denominator you'd have positive 1. So it's an overall positive. So, okay, good. It looks like my profit function is actually increasing. So my expectation, if this is a max, what should the other side be? Decreasing. So let's see if that happens. Let's plug in 10. Okay, so we could actually look at this. So I've got 10 squared is 100, so I've got negative 300 plus would be 60. So I'm still going to have a negative. A negative plus 72 is still going to be negative. Okay, so you got a number right. And then down here, if I plug in 10, I've got negative 1,000 plus, what would that be, 300. Okay, so I'm negative plus 720. Okay, that's still going to be negative plus 1. So I've got an, is that correct? Nope, I didn't do that right. Give me the numbers. Is that positive? So it's going to be like negative 1,000. You have the calculators. 300. Okay, so it is positive, yeah. So I did that too quick. Okay, so I'm going to have an overall negative. And you see how you can check yourself and go, well, the expectation is this is increasing to decreasing. So if we answered this, not yet, we're going to still have to write out something. So I have max profit when how many units are sold? Yep, 6 units are sold. Now, could I figure out what the max profit was? Yeah, what would I do? Yeah, you'd find P of 6. Okay, so that's a good stopping point. You guys have a fantastic spring break. I hope that it is a safe one and you get some work done.